Hello, my name is Tristan. This is Lab 5, the Slinky. Table of contents, introduction, fundamental physics principle, procedure, tracking analysis, potential errors, and what if questions. Introduction. What was the lab? This lab examines the motion of a slinky as it was released and dropped vertically when the slinky is let go. The top begins to fall while the bottom initially remains at rest, creating a unique motion as the compression wave travels through the spring. The motion was recorded using a video and analyzing the tracker to extract position data over time. This data was then used to observe how different parts of the slinky moved during the fall, and how the motion changed as the spring collapsed. A computational model was built then using Glowscreen to simulate the behavior of the slinky using physical laws, allowing comparison between the observed motion and the predicted motion. Purpose of the lab. The purpose of the lab was to determine whether a physics-based computational model could accurately predict the motion of a slinky as it falls and compresses. Additionally, the lab aimed to analyze forces and energy changes during the fall, particularly how gravity potential energy converts into kinetic energy and how the spring internal forces affect the motion of different parts of the slinky, right? Right?
Right.
Yeah. So fundamental physics principles used in Lab 5. Gravity, of course. Right, guys? Gravity, of course. Newton's second law. F net equals ma. Energy principles. The total energy of a system is the sum of kinetic energy, gravitational, oh, bye, guys, spring potential energy. Procedures for the lab. Set up tracker, extract data, build models, and analyze results. The tracker output. You got to set the scale, align axes, track motion, interpret data, and here's the data that I acquired. And here's the code that I acquired. And here's the results. As you can see, the blue is the predicted, while the orange is the observed. Here's the potential errors, the calibration errors in tracker, small inaccuracies in tracking position frame by frame, incorrect estimation of spring constant, relaxed length, and then numerical errors from the time steps of simulation, energy drifted through approximately computer model, all that. What if? Why does the bottom of the slinky remain stationary? The bottom of the slinky stays at rest because the upward tension force from the stretched spring balances the downward force of gravity. Since these forces cancel out, the net force is zero, so the bottom does not move until the tension changes. What if we put a large weight at the bottom? Would it remain stationary? It depends on the slinky. If the spring can provide enough tension to balance the added weight, it will remain stationary at first. But if the weight is too large, the forces will no longer balance, and it will start moving immediately. Thank you.